Okay, molecules with different configurations. So starting with cis-trans isomers and then moving on to sp3 carbons that have their own unique, what we call stereochemistry. So we can think of different conformations of a compound. So these are not the configurational differences. Different conformations of a compound as having the same shape. This would be a Newman projection type of conformation, rotation about a single bond. They have the same shape, but a different orientation in 3D space. So they have the same shape, the same connectivities, but the atoms are in different positions in three-dimensional space when they rotate about a single bond. And so we talk about having a stable configuration, when a dog is standing on all four legs, well supported, and an unstable configuration, standing on one leg. And then we have compounds with different configurations that can be separated. And these are the compounds that we said were cis-trans isomers, or are what we call, or have what we call asymmetric centers. So beginning with cis-trans isomers and their different arrangements in space, this is because there's no rotation, there's no additional movement, and so it's locked in that position. So we have the same components, and the atoms are bonded in the same order. So carbon to carbon, carbon to hydrogen. The cis has the exact same order of bonds as the trans. But they have the atoms have physically different positions in space as a result of not being able to move freely. And so this is their example is that we have all the same components, but position, for example, of a leg and an arm are still connected to the body, but in a different position and space. Cis hydrogens, as said previously, are on the same side of the double bond, and they are vinyl hydrogens. Trans hydrogens are on the opposite side of the double bond. Cis and trans isomerism is only valid when one vinyl carbon has a substituent or group identical to a substituent or group on the other vinyl carbon. So what does that mean? When we look at the cis-trans isomers on the previous slide, you see that we have the cis isomer has one hydrogen on each vinyl carbon, one hydrogen on the first vinyl carbon and one hydrogen on the second vinyl carbon. These groups are identical but on adjacent carbons. This is only called a cis isomer because these two groups are the same but on different carbons. So to have cis-trans isomerism, that is what we recognize, having the same group on two different carbons and then saying, are these two identical elements on different carbons on the same side or on opposite sides? But if we don't have two that are the same, for example, bromine, chlorine, hydrogen, and methyl, how can we say whether it is cis or trans? That term is no longer a valid term because we don't have two things that are the same, which is what we're recognizing. Having the same thing either on the same side as cis or having the same thing on opposite sides as trans. But these molecules are still uniquely different with the same connectivity but spatially different arrangement spatially different arrangement 3D that cannot be changed by rotation. So we have a different system called the EZ system of nomenclature. Z means zusammen, and I like to say it's on the same side to help me remember that Z is same side. And entgegen means opposite. But if you can remember that it's on the same side, then you will know that E is the opposite. So, how do we determine whether something is E or Z? What you do is for each vinyl carbon, it is bonded to two groups. And you are going to rate each group on a single vinyl carbon as being a low priority and the other as being a high priority. And then you're going to do the same thing, rate the priority of the groups on the second vinyl carbon. Once you have listed one group on each carbon as high priority, you will be able to determine if the high priority groups are on the same side or if the high priority groups are on the opposite side and are called entgegen or E. And then we will use those designations in the names of molecules. But what you will see is that these terms are interchangeable with cis-trans, because a cis-trans molecule can also be rated according to the EZ rules. We can take a vinyl carbon in a cis molecule and rate the high priority and the low priority group, and these terms will apply. And so the ACS will use both when describing cis isomers. So a cis isomer is a Z isomer, but a Z isomer is not necessarily a cis isomer. And a trans isomer is an E isomer, but it is not necessarily, but an E isomer is only a trans isomer if there are two identical groups. Okay, so going back, what does high and low priority mean? The priority is assigned according to atomic number. Highest atomic number, highest priority. Well, let's look at some examples. Okay, so here we have an E and Z isomer of the molecule that we're showing has three different groups: bromine, chlorine, and methyl. So we do not have cis-trans that we can name with this. For each vinyl carbon, we need to go and assign a high priority group and a low priority group. The highest atomic number connected to the vinyl carbon will be the high priority group, and the lowest atomic number connected to the high priority carbon will be the low priority group. Bromine has an atomic number of 35. Chlorine has an atomic number of 17. Hydrogen has an atomic number of 1, and carbon has an atomic number of 6. So, for our first carbon, our first vinyl carbon, the high priority group is bromine, because 35 is greater than 1. and hydrogen is the low priority group. For our second carbon, the high priority group is chlorine with an atomic number of 17 that is greater than 6 for carbon. And so both of the high priority groups are above the double bond. We call this Z. On the isomer to the left, the high priority group bromine is on top, and the high priority group chlorine on the other vinyl carbon is below. Thus, the molecule on the right is the E isomer. And to name this molecule, the Z isomer, we would write Z-1-bromo-2-chloropropene, because when we have a double bond, we count the longest chain that contains the double bond with the lowest numbering for all substituents possible. So we would start numbering at the carbon bonded to bromine. That would be 3 carbons in total. The substituents are bromine and chlorine. Bromine would be listed first alphabetically, therefore 1-bromo. Chloro would be listed next. And our suffix, because it is an alkene and not an alkane, would be ENE. Okay, there are more complicated molecules. So here's an example where the first atom bonded to each carbon, each vinyl carbon, is a carbon atom. So I've highlighted in green that these are all carbons. There's no difference in atomic number. So these green carbons cannot be used to determine whether the molecule is E or Z. The next step is to go one bond out and look at the atoms connected to that carbon that is one bond further away from the vinyl carbon. Let me explain. So all the carbons are the same. They have the same atomic number. We can't use them. So we go out to the next atom. What they've written to the side here that I have pointed out with an arrow are the atoms that are bonded to the carbon that is highlighted green. So the carbon that is highlighted green is bonded to 2 hydrogens, 1, 2, and 1 carbon, 3. If you look at the carbon below, this carbon is bonded to 2 hydrogens, 1, 2, and 1 chlorine. Now we finally have a difference in atomic mass, chlorine compared to carbon. Because chlorine has a higher atomic number, the bottom group is the higher priority. For the next carbon on the other side, now that we've determined one vinyl carbon, we have to look at the other vinyl carbon. Okay? So the atom bonded to the green carbon are carbon, carbon, and hydrogen. Say that again. The atoms bonded to this carbon are carbon, carbon, and hydrogen, as stated at the side. On the bottom, the atoms bonded to the carbon are hydrogen and oxygen. So we have oxygen, hydrogen, hydrogen. the atomic number of oxygen is greater than the atomic number of carbon. We compare 1 to 1. We do not add atomic numbers of all of the atoms. No, we take the highest atomic number that is bonded to this carbon and we compare it to the highest atomic number that is bonded to the other carbon. So because oxygen has a higher atomic number than carbon, the bottom carbon is the high priority carbon. And so now we have confirmed that because both of the highs are on the same side, we have the Z isomer. When I look at these molecules, these molecules are normally drawn as skeletal structures. And for me personally, it is easier to determine EZ isomerism with the skeletal structure. So I've drawn above the skeletal structure for the same molecule. I've highlighted the carbons in green, and those are all the same and we can't make comparisons. When we go one bond away, I've highlighted the atoms in blue, and we can see the comparison clearly that chlorine is compared to carbon and carbon is compared to oxygen. We know that chlorine has a higher atomic number than carbon, and oxygen has a higher atomic number than carbon. And so we can see more obviously that this isomer is Z in the skeletal structure than in the condensed form.